Okay, so the first type of integral we're going to look at, quite a general looking expression. P and Q are both polynomials in X. The important thing is that the degree of Q has to be at least 2 larger than the degree of P. And also Q shouldn't contain any zeros on the real axis. Okay, so a very simple example of this is this familiar looking integral here. So here P is 1 and Q is a squared plus x squared. Now this particular integral we can obviously do using the usual integration methods. We can find the indefinite integral, obviously it's arctan, and then use the usual methods. But we're going to illustrate how to do this sort of thing using the residue theorem. So rather than go through all the theory first, I'll just show you how you could do this very quickly. I should say in this solution, I would actually, when you're doing a question like this, I'd prefer that you do a bit more of this sort of thing, showing where things come from. But I'm showing you now in theory how you could do it quite quickly. So the first thing to notice is that P is degree 0, Q is degree 2. So that means Q is at least degree 2 larger than P. So that basically means that the integral exists. A squared plus x squared is never 0 for any real x. So that's the other thing. So we can go ahead and use this technique. So basically the contour we need is this one. The contour goes from minus r to r. We actually take the limit as r goes to infinity, and then this line here is this line integral here from minus infinity to plus infinity is the integral we want in the end. What are we evaluating? Well, we're actually evaluating the contour integral we're evaluating effectively is actually dz. We replace the x by z, and we've got dz and a squared plus z squared evaluated around this closed loop here, which we label as gamma. So gamma refers to the whole thing, not just this semicircle. It refers to the whole closed loop or contour. And the line integral went along this line here because it's the real axis. Dz is equal to dx. So that's, and obviously z along this line is equal to x. So then we get the integral we want along this line. We've got this other integral here, which, as we show above, actually tends to 0 as r goes to infinity. Okay, so the actual work we have to do is to locate any singularities, because basically the integral around this contour is going to be 2 pi I times the residue of any singularity inside. So the only singularity, so we look at this and say, okay, well the function 1 over a squared plus z squared has simple poles at these two places. We only need to consider this one here, and we need to find its residue. We've actually already done that. That was in this example here. We found the residue and found that it's 1 over 2ia. So the answer to the integral, because this bit here vanishes, this integral here as r goes to infinity is simply 2 pi I times the sum of the residues. There's just one residue, just one pole. So it's 2 pi I times 1 over 2ia, and we get pi over a, as we would expect from using ordinary methods. So let's now actually look in detail about why this method works. So what we're trying to show is effectively this formula. I should stress, don't try to remember this formula. This is what we're going to show. This is really showing why this method will work for any P and Q, where the degree of Q is at least 2 greater than the degree of P, and so on. Okay, so we consider the contour integral of P of Z over q of z around the path shown here. So along the real axis, when we're doing this integral, p over q dz, along the real axis, well, there's no change in y. So dz, well, dz we can always write as dx plus I dy. dy is 0, there's no change in y. So dz along here is just dx. So this straight line here is basically just this integral here, which is very close to the integral we're trying to find. The integral we're trying to find is simply when r goes to infinity. So this, when r goes to infinity, will be the integral we want. That leaves us with this semicircular path here. Then we have to change variables. So we've got, this is a semicircle of radius r. We change variables. So z equals r e to the I theta, differentiating. R stays constant. The theta is the thing which varies. So if we differentiate with respect to theta, that brings us an I down. The r stays there, and we have a d theta. So the dz turns into this. That's what we've got here. And now p, a function of z, we just write that function as r times e to the I theta. And the z as r times e to the I theta. Then we think about this integral. Now, if q is of degree 2 more than p, then if you think what's going to happen, we're looking as r goes to infinity. Basically, the highest term will be some power of r, and the highest term of this will be some power of r, which is going to be a power 2 powers higher than this p. And then we multiply by another r, but still we're going to have at least 1 power of r higher here than we have combined here. So as r goes to infinity, this integrand is going to tend to 0, which means in the end this integral itself will tend to 0. So as r goes to infinity, this semicircular line will go to 0, as long as this condition here is satisfied. So we just end up with the integral we want is equal to this contour integral, and the contour integral by the residue theorem is simply 2 pi I times the sum of the residues inside. Okay, so you can now do question 18 and 19. Advice about question 19: simplify your answer. I would, in all cases, don't just leave it as a general formula for any n. And this is really a test of the checks on integrals. This is the first example where some of these things are important. So look very carefully at your answer and think about these things.